This video is for lesson 20-2 about the converse of the Pythagorean theorem. For learning goals, we're going to use the converse of the Pythagorean theorem to solve problems, and we're going to create some Pythagorean inequalities. Let's start by discussing what the converse of the Pythagorean theorem would say. First, I've written the Pythagorean theorem in if-then form. If A, B, and C are sides of a right triangle, then a squared plus b squared equals c squared. We have used this theorem to solve problems about right triangles. And every time we've known ahead of time that we had a right triangle, and then we use that equation. For the converse of the Pythagorean theorem, we're going to reverse the order of that sentence. It would look something like this. If we have a triangle and a squared plus b squared equals c squared, then it is a right triangle. Notice that this sentence is kind of the reverse order of this previous sentence, and that's what a converse is, which was an earlier lesson this year. We can use the converse of the Pythagorean theorem to decide if a triangle is a right triangle. I'll pause the video for you to finish writing out A and B here. Now let's apply this idea and do question C. Use the converse of the Pythagorean theorem to determine whether triangle QRS is a right triangle. Up here in the drawing, we have a kite created by one of Sarah's customers. We want to know if this triangle is a right triangle. Is that a 90-degree angle? We don't know if it is, so that's why I'm putting the question mark here. We can decide if it's a 90-degree angle by using the converse of the Pythagorean theorem. If we fill in these numbers for A, B, and C, and it solves the a squared plus b squared equals c squared formula, then it is a right triangle. So let's do this. 40 squared plus 42 squared, and then over here, 58 squared. We don't know that these are equal, so I'm putting an equal with a question mark. Now let's take a calculator and evaluate these terms. 40 squared is 1600, 42 squared is 1764, and over here on the right, 58 squared is 3364. Adding these numbers together, it is 3364. These are the same. So plugging in those three numbers into the Pythagorean theorem works. This is a right triangle, and we can answer this question yes. Let's skip ahead to question 5 and do another one of these as an example. Use the converse of the Pythagorean theorem to determine whether the following sets of numbers form a right triangle. If a right triangle is not possible, say whether it would make an acute triangle or an obtuse triangle. For example, let's do question B together. So we have 6/7 squared plus 8/7 squared. And we want to know, does that equal 10/7 squared? This first one is 36 over 49. This one here is 64 over 49. Is that equal to 100 over 49? On the left side, these fractions have common denominators, so you add the numerators. 36 plus 64 is 100. And we can see that these numbers do satisfy the Pythagorean theorem, so this is a right triangle. But what if this had not have worked? How would we have known whether it makes an acute triangle or an obtuse triangle? Let's try question C together, over here on the right side of the screen. The smallest number there is what we want to put in for A. So what is the smallest number? The square root of 42 is 6.4. So that's the smallest number, and that's what we're going to fill in for A. So A is the square root of 42 squared plus, now the next biggest number's got to be B, and that's the 20 squared. And then for the letter C, the largest number, 21 squared. Are these equal to each other? The square root of 42 squared makes 42 because square roots and squaring cancel each other away. 20 squared is 400, and over here 21 squared is 441. Are these equal to each other? 42 plus 400 is 442. Well, these are not equal to each other, and what happens is that 442 is greater than 441. So when you look at the two shorter sides and square them and add them together and get a number that's greater than the hypotenuse squared, is that when you have an acute triangle or an obtuse triangle? What's your thought on that? This creates an acute triangle. Let's take some notes on that. When a squared plus b squared is equal to c squared, it's a right triangle. When a squared plus b squared is greater than c squared, it's an acute triangle. All angles are less than 90 degrees. And the third case, when a squared plus b squared ends up less than c squared, that's when you would have an obtuse triangle. So I'll pause the video for you to write down these notes right here. Let's do number 6 and use these notes to answer the question. Sarah's best customer wants to design a kite in the shape of a triangle that has these 3 side lengths. What kind of triangle is it? Is it right, acute, or obtuse? To tell, we're going to use the Pythagorean Theorem and go 27 squared plus 34 squared, and then for the largest number, put that in for C, 45 squared, and then figure out what's the relationship between these. Does the left side end up less than the right, equal to the right, or greater than the right? So let's use a calculator, type these in, and find out. I'm going to pause the video for you to answer question 6. You're trying to decide if it's an acute, right, or obtuse triangle. Adding these together and doing the squaring is 1885. Over here on the right is 2025, and so this is less than 2025. Then looking over at our notes, when we have that situation, we have an obtuse triangle. So this kite has an obtuse angle in it. Next, let's go to the check your understanding. We're going to skip number 7 because we just did some samples, but do number 8. The numbers 11, 60, and 61 are a Pythagorean triple. If you use these as the A, the B, and the C, it works. Use this fact to find 2 additional Pythagorean triples. The idea that we're going to use is that multiples of a Pythagorean triple are also Pythagorean triples. So we can find another triple by finding multiples of these numbers. Like if we multiplied them all by 2, the numbers that we would get are also a Pythagorean triple. So 22, 120, and 122 are 3 numbers that could be sides of a right triangle. Let's find another multiple of that original Pythagorean triple. We could times them all by 3. And the numbers that we get would also be sides of a right triangle. So 33, 180, and 183 would work for the Pythagorean theorem. And we could do this with any multiplier that we wanted and get an unlimited amount of Pythagorean triples, all from knowing that these original 3 numbers are Pythagorean triples. The reason that that's helpful is because if you learn some common triangles that are right triangles, then you can use multiples to get more of them. For example, there's a really famous right triangle. It's the 3, 4, 5 right triangle. Multiples of this are also right triangles, like the 6, 8, 10, or the 9, 12, 15. These are also right triangles. So in this lesson, we used the converse of the Pythagorean theorem. That means we used the theorem in reverse. When we had sides, we were able to test whether the triangle that has those sides is a right triangle.